Hi boys and girls, this is lecture 2.5 in Unit 2. This is the second part of a lecture on the topic of continuity and one-sided limits. On this first slide, we display those topics we discussed in part 1. We came up with a formal definition of continuity. A function f is continuous at c if the following three conditions are met. The function has to be defined at c, the limit has to exist at c, and the limit at c has to equal the function value at c. This is important, boys and girls. Make sure you have this memorized. You'll be asked to use the test for continuity when justifying continuity on quizzes and tests. We also learned that there are two types of discontinuities, removable and non-removable, and we also defined one-sided limits. As previously mentioned, a wide variety of elementary functions are continuous at every point in their domain, including polynomial functions, rational functions, radical functions, and trigonometric functions. Given that f of x is equal to 1 over x minus 6 and g of x is equal to x squared plus 5, discuss the continuity of the following functions. We'll start with the fact that f of x is equal to 1 over x minus 6. Let's discuss the continuity of this function. It's a rational function, and we know that it's continuous everywhere in its domain. However, there is a number that's excluded from its domain, and that is 6. We can't let x be 6 because if we did, the denominator of this function would be 0. Now, since there is no analytic way to rewrite this function in order to find a limit, let's take a look at the graph. As expected, there's an asymptote at x is equal to 6. We can see unbounded behavior to the left of 6, unbounded behavior to the right. So this function is continuous everywhere except at x is equal to 6. Now let's look at letter B, which asks us to discuss the continuity of g of x. G of x is a polynomial function, x squared plus 5. We know that a polynomial is continuous everywhere on its domain. Well, a polynomial function is defined at all real numbers, so we would believe that this function is continuous on its entire domain. Of course it is, but let's take a look at the graph to verify our results. Here's this polynomial function. You can see it's a quadratic and the y-intercept is 5. There are no breaks, no discontinuities on this graph, continuous on the entire real number line. Finally, let's look at f of g of x. It's a composite function, so we first need to determine what this function looks like. We're going to take g of x, which is x squared plus 5, and plug it in for x in 1 over x minus 6. This gives us 1 over x squared plus 5, that's the g of x function, minus 6. When we simplify this, we get 1 over x squared minus 1, another rational function. And as we know, rational functions are defined everywhere on their domain. Well, where is this function not defined? Since this denominator equals 0 at 1 and at negative 1, we have to exclude those values from the domain. Therefore, we are going to expect to see discontinuities at 1 and negative 1. So as we take a look at that graph, we see the expected discontinuities there, vertical asymptotes at negative 1 and at positive 1. So this function is continuous everywhere on its domain, which excludes 1 and negative 1. Thus, the only discontinuities occur at 1 and negative 1 for this function. Let's look at a definition of the intermediate value theorem. If f is continuous on the closed interval AB, and k is any number between f of a and f of b, then there is at least one number c in the interval AB such that f of c equals k. Let's see what that means by looking at this graphical depiction of the intermediate value theorem. Notice on the x-axis we have the interval a, b, and then of course function values represented as well. The function value at a is f of a, this point. The function value at b is f of b. The intermediate value theorem is saying that if this function is continuous, then every value between f of a and f of b has to be represented from the interval a to b. For example, if f of a was 10, and let's say f of b was 4, if the function is continuous, doesn't it stand to reason that every number between 4 and 10 is going to be represented in this function? It might be represented more than once if this function had more curvature than the one I've displayed here, but the intermediate value theorem says every value must occur at least once. Therefore, there must be a value between a and b which generates every function value between f of a and f of b. So the idea is any k that you choose between f of a and f of b must exist. Therefore, a value between a and b must generate that function value. That's the intermediate value theorem. This theorem tells you that a value exists in the interval, but doesn't provide a method for finding the value. Thus, the intermediate value theorem is what is referred to as an existence theorem. We know that a value exists here between a and b, which would generate every function value between f of a and f of b, but we don't necessarily have the ability to always find that value. That's what it means by existence theorem. Now, remember that a function that is not continuous does not necessarily display the intermediate value property. It could, but it doesn't necessarily do so. Notice I've shown here a discontinuous function at the point C, and again I have an interval a to b, f of a to f of b. Once again, if this is a 10 and this is a 4, in this situation, are we guaranteed that every single number between 10 and 4 is represented on the graph? And we have to say no because of this break in the function. We can see that there are values that are missing. Therefore, the intermediate value is not necessarily going to apply when the function is discontinuous. Here we have an application of the intermediate value theorem. Use the intermediate value theorem, IVT, to show that the polynomial function f of x equals x squared plus 2x minus 1 has a 0 in the interval 0, 1. First, we're going to want to know what the function values are at the endpoints of this interval. What is f of 0? When we plug 0 into our function, we get a function value of -1. What is f of 1? When we put 1 into the function, we get 1 plus 2 minus 1, which is a function value of 2. What does this mean graphically? At 0, we have a function value of -1. At 1, we had a function value of 2. To get from -1 to 2, we had to cross the x-axis somewhere between 0 and 1. There's no way to get from -1 to 2 without crossing the x-axis. However, are we guaranteed that this occurred? Are there any breaks or holes or jumps in the graph which mean that maybe somehow we got from -1 to 2 without having a function value of 0? That depends on the continuity of the function. Do we have continuity between -1 and 2? As we look at the original function, we see that it's a polynomial. A polynomial is continuous on its entire domain, which is everywhere. Since we are guaranteed this continuity, we are guaranteed that at some point the function value is 0. In fact, we're guaranteed every number between -1 and 2 on this particular interval. Furthermore, there are x values which must create the y values that we're discussing. That's what the intermediate value theorem is saying, that there's guaranteed to be x values between 0 and 1 that are generating every function value between -1 and 2, including, of course, 0, the one that we were looking for. So there is an x value guaranteed to us that is generating a 0 between 0 and 1 on the x-axis. We don't necessarily know what it is, but we know that it exists. That's why this theorem, the intermediate value theorem, is known as an existence theorem. Here is the actual graph of this function, and we can see that it verifies our results. That's it for today's lecture, boys and girls. Galileo said it best: math is the language God used to write the universe. God bless you, boys and girls.